I want to welcome you to my lecture today. Of course, today the focus is going to be on probability concept. We started this topic on Wednesday, and of course, we're going to continue from where we stopped. So today, in the outline, I'm actually going to make a distinction between theoretical and experimental probability. Okay, I'm also going to walk you through some uh, probability rules that we call axioms. Then, because for you to be able to figure out what probability formula you're going to use in a particular, given a particular question, then you need to be able to understand the type of event because the type of event we actually determine the probability law or rules that we're going to apply. Then because of that, I'm going to walk you through the different type of events that we have. Okay, so let's get started. Why do we find ourselves, okay, studying probability? Of course, I told you the other time, uh, we live in a world where there's variation. And of course, we want to understand our environment, want to understand our political environment, economic environment, and so on like that. And because of the fact that there's variation in environment, probability thrives in variation, and we need to be able to have a probability skill or knowledge to be able to understand what is going on. Now, when you're working with probability, you need to be able to understand whether you're working with a theoretical probability or you're working with the experimental probability. I'm actually going to explain this in the context of what happened. If you really want to have the understanding of the reason why the Federal Reserve cut interest rates. Okay, I know some of you will be more, be wondering, you really want to understand probabilistically why that happened. I'm actually going to tell you where their decision falls on the theoretical probability side and on the experimental probability side. Don't forget, I said something the other time. To understand what is going on in our environment, okay, we need to be able to use the mind of probability. Now, when I talk about theoretical probability, the theoretical probability is actually talking about calculating probability or putting into consideration possible values. I'm going to say that again. Theoretical probability arise when you compute your probability based on possible outcome, without you conducting actual experimentation. Okay, it's more or less like you base it on theoretical belief. You have a coin. Before you toss a coin once, you already know the probability, even before you toss the coin. That's theoretical. So that probability is going to be 1/2 because you got two sides in a coin. Okay. Now, if you toss flip a die, of course, because you have 6 sides in a die, of course, even before you flip it, the probability is actually 1/6. Those are theoretical. Okay. But the experimental probability, on the other hand, it means you base your computation of probability on experimentation. You conduct a trial, okay? And based on what you see, you figure out the probability. You can say the two are not the same. And let me tell you this. I'll quickly go into an example of flipping a coin. The theoretical probability is going to tell us flipping before you even flip a coin at all. It's going to give 50-50% chance to decide. But when you go into the coin and maybe you flip the coin 10 times, when you are flipping the coin, you perform an experiment. If you flip it 10 times, there's possibility you may see 7 head. And the probability of head in that situation will be 7/10. Now, take a look at that. Experimental probability has a conflict now with the theoretical probability. The theoretical probability assumes that it's going to be 50-50. The theoretical probability assumes that when you flip that 10 times, the numbers of heads should be 5. That's theoretical. But experimental probability, you may get something different from that. But let me tell you this. On the long run, experimental probability converges to theoretical probability. Does that make sense? On the long run, they converge. Now, I want to apply this to economy. You know, why the Federal Reserve in the United States cuts the interest rate. I actually want to explain that now using theoretical and experimental probability. I want to start with theoretical. You know, in theoretical, you make use of predictive model, okay, which is theoretical model. And the Fed, they actually believe that the only way they can cut the interest rate is actually depend on how economy reacts to certain stimuli that I'm actually going to call inflation rate and exchange rate of GDP and so on like that. Now, they could have it that when the when the inflation rate is very close to 2%, they actually have a threshold, and the unemployment rate is high, then the model could predict the probability that they're going to cut the interest rate maybe 80%. That is theoretical. Okay? But let us go experimental. The experimental is going to be if in the past, okay, if in the past the inflation rate was below 2%, and out of 10 times in the past, they only cut the interest rate 6 times out of 10 times. That is experimental probability, which is going to be 6/10, because it is not all the time that inflation rate go below the value that they cut interest rate. Okay, and of course you can see why what I talked about experimental here, because when you make use of when you look at the inflation rate from July to August as going by the labor, the Bureau of Labor Statistics, in July was 2.9%, but in August was 2.5%. And they believe that 2.5% is very close to the 2% margin. And not only that, if you look at the employment rate, okay, it's a little bit high as well. And that was the justification. They are actually using the theoretical model. The theoretical model, which is theoretical probability. Now, I want to move away from that. Now, whether theoretical probability or experimental probability, the probability of an event is a ratio. And it is going to be the ratio of the event favorable divided by the totality. A philosopher said, and I quote, "Our mind can never be empty." Okay? We always have something occupying our mind. Okay. When you want to figure out the probability of what we have in mind from occurring, it's going to be the number of times what we have in mind occur divided by totality. So right now, that's why you see the probability of A equal to the number of outcomes in A divided by the total number of outcome. The probability value can be in fraction. That's why you see 1/2, can be in decimal, and can be in percentage. Okay, for interpretation, I think we normally use percentage most of the time. Okay, now I need you to take a look at this. In a bag, you have 3 red marbles, 2 blue marbles, and 7 yellow marbles. There's variation in terms of color here. And of course, you want to figure out the probability. If a marble is chosen at random, what is the probability is going to be red? Okay, now this is theoretical because you did not perform this experiment. You have a bag. It's whatever bag that have 3 red marbles and so on like that. So the probability of red here is just going to be the numbers of red divided by totality. Okay, now let's look at this. We want to see whether it's experimental or theoretical. Okay, Prentice went fishing. Look at that. He went fishing at a pond that contained 3 type of fish. Blue jays, he caught 40. Oh my God, he's experimenting. Okay, now, if you take a look, it took record of the numbers of blue fish he caught, numbers of red, and so on like that. And you can see the numbers of time is actually the frequency. When you hear something about probability, don't be scared. Okay, don't be scared. The probability is just trying to say, oh, before I can apply that, there's variation. As you can see, variation in fish type. And a particular value that will appear in another column is just going to give us the numbers of times or each of that occur. Okay, that's what you see. Now here, if you catch a fish, we can figure out the probability that is a blue gill or a red gill or a whatever. So if I want to figure that out, of course, 13 over the total for blue gill, 17 over the total for red, and 10 over the whole thing for that. So this is an example of experimental probability because that was actual experimentation. Okay, another example of experimental probability now. Okay, you flip a coin. You flipping a coin means you're performing experiments. Okay, now you flip a coin and you flip a fair coin, okay, 30 times, and you get 17 head. Of course, the probability of head is going to be 17 over 30. Can somebody tell me for extra credit, if this were to be theoretical, okay, and you have out of 30 times, how many head are we expecting? Okay, I'm saying, you know what I needed to do? I just need to call your answer at the same time. What is it? What is that? Send me a message for extra credit. You guys are fantastic. All of you that you meant, I need you to be sincere. Those people that talk, send me a message for extra credit. That will be 15. That will give equal chance. That is theoretical. But experimental, you can see what we have. But like I said, when you continue to flip the coin so many times, we expect, the experimental probability value to converge to the theoretical value. And that's why we normally encourage taking large samples. But you know what? In this class, I'm actually going to tell you how large is the large. Okay, I want to go into probability axioms. I want to stay in the Minnesota. I want to live in the state of Minnesota, and I don't want to get into trouble. Then I need to be able to understand the rules and regulation in the state of Minnesota. Oh, I want to use probability. I want to solve problem with probability. then I also need to be guided. I need to know the rules. What are the rules that guide probability? When I talk about axioms, I'm talking about rules. Okay, let's talk about those rules now. Basic rules in probability. So what I'm going to do now, when E is an event, and this event has some element in it, and I want to figure out the probability associated with the event. Like, I want to know what is the number of times events occur relatively to the totality. Okay. Now, we got a boundary on that. The probability of, of the event E has to be between you get into trouble. Then I need to be able to understand the rules and regulation in the state of Minnesota. Oh, I want to use probability. I want to solve problem in probability. Then I also need to be guided. I need to know the rules. What are the rules that guide probability? When I talk about axioms, I'm talking about rules. Okay, let's talk about those rules now. Basic rules in probability. So what I'm going to do now, when E is an event, and this event has some element in it, and I want to figure out the probability associated with the event. Like, I want to know what is the number of times events occur relatively to the totality. Okay. Now, we got a boundary on that. The probability of, of the event E has to be between 0 and 1. Between 0 and 1 is trying to say that, okay, you know what? If the moment you get a value outside the range, that can never be probabilistic value. Okay. When you're close to 0, when your probability is very close to 0, you're moving towards uncertainty, perfect uncertainty, and very, moving close to 1, you're moving toward uncertainty. So I just wanted to make use of that to, take note of that. Now, rule number 2 is talking about the probability of a sample space. You remember the other time, sample space is a collection of possibility, right? Now, why do we say the probability of a sample space equal to 1? Because it's so sure that at least one event will occur. Okay, somebody who is going into a business, profit and loss are the elements in the sample space. At least one of that will occur. Okay, so the probability of a sample space equal to 1 means a sample space is a sure event. Okay, does that make sense? And that very 1 means 100%. It's like you've considered everything. Okay, now I want to further move to I want to walk you through further axioms now. So take a look at number 1. Like I said, when we have an event E and it's a subset of a sample space, okay, I'm actually going to be taking that event E. I can take event E to be the student in this class. Y as a sample space is University of Minnesota. Okay, now this class is a subset of the University of Minnesota. Okay, now the probability that we're going to have students in this class, okay, is when the probability is greater than 0, then it means we got student in this class. If probability equal to 0, then there's no students in this class. Does that make sense? That's what we mean by probability of E greater or equal to 0. Now, the probability of S equal to 1 means, of course, in the University of Minnesota, during academic section, we expect to have students in at least one class. Okay, now, if you go to number 3 now, I need you to pay attention to number 3 now. Okay, now, the law number 3. When you see union EI, it's trying to talk about E1, union E2, union E3, up to maybe EK. It's talking about events that are mutually exclusive. Okay, I'm actually going to say classrooms in the University of Minnesota are mutually exclusive because the classrooms don't overlap. You cannot be in this class and be in another class at the same time. Okay, now if I want to find the probability of the union of the classes in the University of Minnesota, then because of the fact that no overlapping, then we expect if I choose any 2 classes I expect this to happen. EI intercept EJ have to be 5. Maybe I choose this class and I choose another class and I compare elements in the two classes, then they will not have anything in common. Okay, for if they are mutually exclusive event. And if I want to find the union, then all what I just need is to add up. I need to find the probability of this class, find the probability of another class, then of every other class, then I'm going to add them up. Okay, so if I add them up, then I'm actually answering the question that has to do with the probability of E1 union, E2 union, E3 up to that. Now, I also needed to pay attention. Let me tell you this. I understand my probability because of the fact that I like relating to real life. Let me say this. My dad, my late dad, my mom, none of them can write 1. None of them can write 0. Like they didn't go to school. But if I learn when I was in college, if I learn statistics or rigorous mathematical concepts, if I can explain that to my mom that didn't go to school and she understand, then I can explain to anybody anywhere in the world. That's my belief. So what am I trying to tell you? When you are seeing this notation, let me tell you what I was paying attention to. I don't just do maths, I don't just do stats, but what is behind this notation. If you pay attention to what is behind notation, you're actually going to be fine. Now, this time around, right now, you know what I want to do? We actually want to revisit the rules that connect a sample, a particular set A and an empty set and the entire set. Now, let's take a look at the first one. The first one, I'm going to take A as a non-empty set. Let me take it to be this class. And phi to be another class that is empty. Then, if I look at the union between the two, it's like adding them, I'm still going to have this class. That's why I have A. Does that make sense? Okay, I want to go to 2 now. 2 is, do they have anything in common? Okay, there is going to be empty. 2, that was why I got this. Now, I want to come to the third one. Right now, I want to, let's say that A, because A is a subset of X, okay, X is bigger than A. I'm actually going to see more practical example now. I'm going to call A to be state of Minnesota. And I'm going to call S United States. If I had Minnesota, state of Minnesota to the United States, of course, I'm going to have United States. That's why you see A union S equal to S. Then the last one, if I look at the common, what Minnesota and United States has in common, okay, then they have Minnesota in common. Does that make sense? That will enable you to understand what we're talking about here. Now, where we are now is very, very crucial, and I need you to pay attention. My experience in teaching this course. Go ahead. I should, yeah? Yeah. Oh, okay. You really want to? Yeah. Yeah. Okay. Now, let's talk about, now, this area that I want to talk about is very, very crucial because my experience in teaching this course. I realize that students have issue with probability because from a given question, they find it difficult to identify the type of events. The type of event will determine the probability formula. I'm going to say that again. The type of event determines probability formula to be used. And that's why I want to walk you through the type of event we have and the corresponding probability formula that goes with each. I want to start mutually exclusive. Now, I want to start this from 2 contexts from events A and B. It could be more than 2 events. Now, what do we mean by mutually exclusive? Event A and B are said to be mutually exclusive if they cannot occur together. The occurrence of one will prevent the occurrence of other, which means you can, it's either you are in this class right now or you are in another class. Does that make sense? You cannot be in 2 classes at the same time. Or let me just say physically, because somebody may want to say, okay, what if I'm in this class physically and I'm in the other class virtually? That's not what I'm saying. I'm talking about physically right now. And now the intersection between the two will be empty if they are mutually. You can see using the diagram, okay, they are disjoints. They don't come together. Okay, that's why you see that. Now the intersection between them, any 2 mutually exclusive event will be empty. And if the intersection is empty, if I want to find the probability associated with this, then the probability of emptiness is 0. Does that make sense? The probability of emptiness is 0. Okay. Now, I need you to listen now. If I'm talking about mutually exclusive event and the question of probability comes up, if I've identified them to be mutually exclusive, okay, then that will attract addition law. Okay, if I want to find the probability of A union B, I'm actually going to use addition law. Okay, I'm using addition law because A and B are mutually exclusive. When they occur, it will prevent B from occurring. So the union, the probability of the union is adding them, finding the probability of A, finding the probability of B, then you add them up. But if you want to find the probability of their intersection, then that will be equal to 0 because A intersection B is empty because they are mutually exclusive event. Now, this is in the context of 2 events that can also be generalized to more than 2 events. When you take a look at a die that have C size, the probability if one shows up, that has prevented others from showing up. Does that make sense? Now I'm going to go in. I want to leave United States now. I want to go to Canada. We are in Canada now. Now take a look at this question. Okay, we're in Canada now. Okay, if you take a look at this, we have data on party supported. Okay, with corresponding percent support. Okay, conservative, liberal, NDP, green, and all of that. Okay, now if I have this is trying to tell us there's variation. Okay, in terms of political ideology in Canada, variation, there's conservative, liberal, and that. And I conducted a survey, okay, and 38 for conservative, 27 for that. Now, based on what I have here now, okay, if I meet an individual Canadian and I know nothing about the person, and I want to base my prediction now on this particular data. So what is the probability that the individual is conservative? It's just going to be 38 divided by totality, which is going to be 38%. Okay, in decimal, you have 0.38. What about individual that support green? Just going to be 9. You can see what I'm actually using now. Okay, now, and if you take a look at this, okay, party supported are mutually exclusive because it's either you are supporting conservative or you are in liberal or you are that. Okay, now if I now go to coin example, okay, to coin example, when it was a coin, we got 2 sides in a coin, and if I want to go by way of theoretical probability, the probability of each is going to be half. if I add them up, if I want to find the probability of the union between head and tail, because head and tail are mutually exclusive, I'm actually going to add them up. And that's why you see me doing here. I added them up because they are mutually exclusive, and that will give me 1. Okay, if I want to extend that to 10-sided die, a 10-sided die that has 0 to 9, okay, if you count from 0 to 9, that would be 10, right? Now I'm going to give equal probability to each and every one of them, which is going to be 1 out of 10. Okay, so when you have 1 out of 10, if I want to find the probability of the union of all of that, so I'm actually, that's going to be probability of 0 plus probability of 1. If I add them up, 1 over 10 plus 1 over 10 plus 1 over 10 plus 1 over 10 in 10 places is actually going to be 1. Okay, now if I go back to the Canadian example, if I had the probability of each, all of that together, maybe because I want to find the probability of conservative, union liberal, union NDP, union that, I'm also going to add all the probability because they are mutually exclusive, and that will give me 1. That's exactly what I'm doing. What I'm doing here. Let me tell you this. Probability is the most simplest topic in the world, but it's going to be so simple if you pay attention to detail. Well, like, what is the essence of what we're doing? Okay, now I want to go. Now I've explained mutually exclusive, and you saw the law, the probability formula that come with that. But right now, I want to move away from mutually. I want to go into non-mutually exclusive. And what do I mean by non-mutually exclusive? The non-mutually exclusive is going to say if I have 2 events, okay, if I have 2 events, it's either event A occur or event B occur, or they both occur together. Look at that. Okay, this occur separately, B occur separately, and they also occur together. I like giving this example. Let's say, for instance, I order for food from 2 different restaurants. Maybe I'm in my house, and maybe I order from Wendy's. I also want, order from KFC, and I want to figure out the probability that at least 1 will arrive on time. Okay, I'm actually going to have 3 possibilities. Number 1 possibility is either the one that I order from Wendy's arrive first, or the one that I order from KFC arrive first, or I looked through my window and I saw 2 drivers. Okay, they arrive at the same time. That's possibility. Whenever that happens, that's a non-mutually exclusive. So non-mutually exclusive is going to say they can occur separately. They can also occur together. Now, if that happens, go ahead. Okay, so you're trying to say maybe we can attribute that to a win, a tie, and a draw. That's kind of close. Yeah, that's kind of close because you're trying to say, but I'm not going to say you should use it in that direction. Okay, but look, this is the deal. The deal is I got 2 events, and I want to figure out what is the probability that at least 1 will occur. Now let's look at the possibility. It's either this occur, or this occur, or the 2 occur. Does that make sense? That is the idea of non-mutually. Go ahead. Oh, okay, you say that again. Exactly. Oh, that's another possibility. No, we're talking about coming the one that will come first. So if I say the one that come first, okay, is either that guy come first, or the other one from another one come first. I'm emphasizing on first, or the 2 of them come together. Now, just like what you said now, there's another possibility that They don't show up at all. That is what you're trying to say. Where's it going there? Okay, that's a different one. Okay, that they don't show up at all. The two of them don't show up at all. But this time around, we're only interested in events occurring. Either this one, or this one, or they both occur together. That's a good question too. Okay, now, what is the implication mathematically if I want to answer a question that has to do with non-mutually? Now, we're going to use this formula here. If I want to figure out the probability of A union B. Now, what have we introduced? We have introduced both. We are subtracting both. Initially, under mutually, we only consider this and this occurring separately. But now, we are incorporating this. So, which means under mutually, this guy is 0. Does that make sense? If I plug in 0 here, I'm only going to have mutually. And you know, I told you the other time, we talk about events that are mutually exclusive, the probability of the interception will be 0. You know that? Okay. Now, that is the formula. Now, I want us to apply that here now. You know, I show you this data set. You collected data on 2 categorical variables. You conducted survey on major of the student and the Excel skill. Okay. Now, when you see a table like this, okay, there is possibility for non-mutually in every contingency table like this, a table that is cross-listed. I cross-list one variable against the other. You know why? There's possibility somebody here is an economist major. There is possibility somebody here has high Excel skill. There's another possibility somebody can be an economist major and also have high Excel skill. That's a non-mutually, right? Now, let's go to the question now. You want to find the probability of a randomly selected being an economist major or having high Excel skill. I need you to pay attention to that conjunction or. Whenever you see or, then junior will come in. It means you want to find the probability of E union H. And that will be non-mutually. So which means I need to figure out what is the probability of being an economist major. That can occur separately. What is the probability of having high Excel skill? That can also occur separately. And what is the probability that an economist major can have high Excel skill? Does that make sense? Now, what I'm going to do, if I want to get the economic major now, I'm just going to go back to the table. Okay, economics major, that will be 24 over 46, right? That will be 24 over 46. Okay, then for the high Excel skill, that will be 6 over 46. Okay, then for both, okay, it is this two. Look at these two here. This is a point of intersection between high Excel skill and economics major. So that 2 over 46 is what I'm going to subtract. And that's why you can see that. You can see this guy now. 24 over 46 plus that minus that. And at the end of the day, this is what I got. Okay. Now the same thing also applicable to what is the probability of business or low skill. Okay, you find the probability of business, you find the probability of low skill, you find the probability of the intersection between the two. Okay, I'm done with the non-mutually. You can see for mutually, we got a formula associated with that. For non-mutually, we got a formula associated with that. Now, right now, we want to go into independence. Okay, independence. Events are said to be independent if they can occur together. Does that make sense? Okay, if they can occur together, like right now, you are listening and I can see some student writing. Those two events can occur simultaneously. And if they can occur simultaneously, okay, and what we want to figure out is how do we find the probability of interception? Now, whenever events A and B are independent, that will attract a multiplicative law of probability. Multiplicative law. So which means we're actually going to multiply the probability of A and the probability of B. Let's go through an example. I actually want to roll a die and flip a coin at the same time because they are two different entities. Then events in coin and events in die, they can occur together. Okay, so if somebody now asks, what is the probability of getting head and 6? Please pay attention to hand, conjunction hand. Whenever you hear about hand, that's an intersection. Does that make sense? And whenever you see or, that's a union. Okay, now what I'm going to do here is the probability of head and 6 will be equal to the product of probability of head multiplied by probability of 6. What is the probability of getting head? Okay, it's going to be 1 out of 2 in a coin. What is the probability of getting 6? In a die, you have 1, 2, 3, 4, 5, 6, right? Okay, and each of them has equal probability. That is going to be 1 over 6. Then I'm just going to multiply. Now, this guy now, 1 over 12 now is the probability that when I flip a coin and a die, okay, the probability I'm going to get a head and getting a 6. Now, what is the probability of getting a tail and a 5? Okay, it's still going to be the same. Now, when you're talking about independent events, the takeaway is if events are independent, they can occur together, and the probability rule, the law, what you're going to use is going to be multiplicative law, not addition law. Multiplicative law. Now, I want to move from that to dependent event. Okay, you can see I want to move from that to a dependent event. When I talk about dependent event, what do I mean? You have a situation whereby what you're going to do now depends on what you've done before. Okay, that's what we mean by dependent event. And let me tell you this. The difference between independent events and dependent event has to do with the way you sample. For independent, you sample with replacements. For dependent, you sample without replacements. What do I mean by sampling with replacement? When you come here, if you're working with a die, it's always going to be 1 over 2. If you're working with a coin, it's always going to be 1 over 2. With a die, it's always going to be 1 over 6. That probability will be constant from, it doesn't matter the number of times you flip, okay? Because you sample and you replace. But situation where you don't replace, okay? When you don't replace, the totality will decrease by 1. And not only that, a particular group will also go down. Now, take a look at this. There are 6 black pens and 8 blue pens in a jar. If you take a pen without looking and then take another pen without replacing the first, without you are sampling without replacement, okay, what is the probability that you get 2 black pens? Now, initially, the probability of choosing a black initially is going to be 6 out of the totality of black. I mean, totality of the whatever in it. So which will be 6 over 14, which is going to be simplified to 3 over 7. Now, you want to go again to choose the second black, but don't forget, you didn't replace the first one. Now, you are never going to have 14 again because you've chosen one. The totality now is going to be 13. And not only that, the number of black will also go down. And that's why you have 5, you have that. Now, let me now tell you, if I want to find the probability of black in the first trial and the black in the second trial, whether I'm talking about independent events or I'm talking about dependent events, the two of them attract multiplicative rule. I'm going to say that again. Whether I'm talking about dependent event or I'm talking about independent event, the two of them attract multiplicative rule. But the difference between that is just going to be if I'm sampling with replacement and I choose black first and I choose black second, the probability is going to be the same. It's going to be 6 over 14 times 6 over 14. But if I choose and I don't replace, I expect the population of that characteristics of interest to go down, and not only that, the totality is also going to go down by 1. But in the two scenarios, whether dependent or independent, I'm still going to multiply. Does that make sense? Okay. Now, and that's exactly what I mean. If you take a look at what we have, if I'm talking about independent, okay, I'm actually going to have this. But if I'm talking about dependent, the second one here is going to become the probability of B given A. I wanted to take a look at it too. I think I'm going to highlight that for you to be able to see what I'm talking about. Okay, please take a look at this guy. If you look at the first one, the probability of A and B equal to P of A times P of B, that is strictly independent, where you are sampling with replacement. You choose, then you replace before the subsequent selection. But if you are sampling without replacement, okay, the probability of A will stay the same, but probability of B is no longer going to be probability of B anymore, but it's going to be probability of B given A. Does that make sense? Okay, that is what I mean. Now, look at this dependent example. 2 cars are selected from a production line of 12 where 5 are defective. Find the probability that both cars are defective. Okay, now if I want to find the probability that both are defective, which means defective in the first, defective in the second, and I need to be able to know how many defective do we have in general out of the totality. That will be 5/12, which is this guy here. So the probability that the first car is defective is that. But when I want to choose the second car, I did not replace the first. Because of that, what do I expect? I expect, even if I'm choosing defective again, the 5 is not going to be 5 anymore. It's going to go down by 1. And not only that, the totality also going to go down by 1. So which means if you take a look at this guy here, okay, this guy actually means the probability of B given A. Okay, the probability of B given A means before the occurrence of B, okay, A has occurred, okay, that is what this guy means. Now I'm going to multiply this by that, okay, but situation where I replace, of course, the second one is still going to be 5/12. Does that make sense? Okay. Okay, I don't want to rush you. I'm actually going to continue from conditional probability in the next class. Is there, okay, if you have questions, you can come over, okay? That's all what I have for you today. Make sure you all stay safe and have a lovely weekend.
Like explain if it's ever. I've seen that marijuana. Yeah, I said that.
Wait, you guys get your
It's squarely.
we don't get ours graded.
And like I thought I did good too, and then 73% or 73.
I was.
Yep.
But then it got to dependent events.
It's like
The variable for that. I mean, normally like. Yeah.
No,
Based on what you have.
It's an hour. We can wait an hour. So that's already before like.
I'm probably gonna start like, we're taking next like hour and then take.
Let's see, after
Yeah.
that fight, take 1 hour.
Yeah.
I would've taken it yesterday, but I was just doing a lot of
Like,
studying.
is there like a specific formula for that?
Yeah,
Basically,
the,
right.
well, the formula, no, the formula is just like,
Make sure.
oh, B given here is already telling us information and the reduction in this.
Right. Alright, yeah, I was just wondering if there was like a formula.
Yeah, no, the formula like this is just, so in the case of dependent, find probability of A and B. It's gonna be probability of A, not times probability of B, not times this one. So that will be for independent, it's just gonna be down.
Yeah.
So the two of them are multiplicating. Right.
I just have questions. So I think, did I do wrong? Because I just screenshot my marks, but it would be possible to save this because I don't save it. It's- I think it's great. I'm really completely
Now, do you want to follow, the same way the coding was done on lab? Yeah,
yeah.
so if you follow that, you should be fine. Or you can just like, just box, plots and put the data. It should just, I think it should be able to, yeah. You can try that.
You can also follow the outline on the
Yeah.
lab and just do the same thing. with
Mhm.
different tabs.
If you just do the same, like, the different is just your data.
Yeah,
Okay.
because the codes were in there. in the
Exactly.
lab.
Mhm.
Yeah, I was trying to follow. I think because this is supposed to be a side by side plot thing. So I'm just.
And you know, at
There's
times,
also a TA.
thank you for that.
Between the, like. you do
Because it's another thing is it's sensitive the moment you,
Yeah.
maybe instead of you putting a lowercase or a
Instead
full
of-
and all, just, it's not gonna run. Yeah,
And
how is
these are at the
sensitive?
very
At
end.
the very end.
Yeah,
Oh,
thanks for sharing that.
thank you.
You know.
Okay.
Okay,
I just have a question on the fly, because I don't have anything but answer this question, just because I think in my head, there's two possibilities for it, because theoretically, there's a possibility, there's a lot of people that watch like a pretty average amount, I'll like give it 3 hours, and then like there's people that watch a lot more, but at the same time, my other thought process is there's people that watch like a central amount, and then there's kind of like equal amounts that watch
If
either
you
less
look
or
at
more.
the histogram in the textbook, it shows that it's actually right skewed.
Oh, it does.
Yeah.
Okay.
yeah, that's why that textbook is also,
Okay.
but let me tell you this, you can also be right because things are changing,
Mhm.
but we know things are changing, but what do we believe right now?
Thank you.
Because that was my same thought on children of
Think
household.
about this, like,
Because
I
like,
was
if you go to
looking
a
at that, I was
developing
like, yeah, I was
country,
like,
Yeah,
they have
yeah.
a ton more kids.
You are right.
But if you go to like a
the
developed
developed
country like the
country,
US or
yeah,
Great Britain,
Different.
it's actually right skewed, so
Yeah,
it
okay.
depends
And,
on.
and what she said now, if you are making an argument,
Mhm.
since you have like two different things in mind,
Mhm.
you can put it down.
Oh,
Yeah,
okay.
you can put both.
And
of
you say,
them.
you can put
Okay.
both, it's okay
Perfect.
for this, just like what she said now.
Okay.
Fantastic.
Thank you.
Statistically, there could be
Yeah, that's
multiple
what I, because
options.
I was looking at some
Exactly.
of them and I was like, I don't know.
You just have to be able to back your argument.
Yeah.
Mhm. Okay.
So for this sample,
Yeah.
is it like 100%, like if you were to put it into like decimal form,
Yeah,
it would
so-
all go up to?
Exactly, so that very one means 100%. So that zero means it's 0%.
Yeah.
Yeah, That's
Okay,
what it means.
and then what does the U mean?
Oh, union.
Union?
Yeah, union is like you're
'Cause I
talking
was
about
seeing that
this or
before.
this.
Okay,
It's not gonna be you, it's going to
Does it-
be,
mean if they like overlap or not? in a
exactly.
sense?
No, the union is talking about what is this or that. This or that.
Okay,
So that this or that happen. So whenever that comes up, that's union. And this or that, depending on whether they are mutually exclusive, if they are mutually exclusive, I'm just going to add the probability of if I want to find union. So this is what I can find union, I can find interception for whatever types of event.
Mhm.
So if I'm talking about mutually exclusive event, okay, I know my interception, the probability will be 0.
Yeah,
But for union, then I'm adding up. So the idea of the union is just like either this or that. That's
okay.
what it means.
But if it's up, does that mean that, because there was up and then there's down, which they probably mean different things.
Yeah, maybe you're talking about the interception, right? Give me, this one. That's an interception.
Okay,
So this one means conjunction, and, A-N-D. A-N-D means they can occur together. What is the probability of the joint occurrence?
okay.
That's what that means. The probability of the joint occurrence.
And then if it's up, then it means the probability of them.
What do you mean by all?
See,
Is it a sign? Which one?
well, see, it goes like this,
Okay,
or it goes like
oh, like that,
this.
okay, so if it is, so you mean this up, right?
No, that's
Oh,
down.
that's down, okay, this down now is talking about hand. The probability that they both occur together.
Yeah, and then if it was the opposite way,
Then
it
it's
would be if
probability
they
that-
don't occur together.
No, it doesn't mean that. It
Okay.
means that it's, what is probability that either this occur or this occur?
Oh, so basically this means non-mutually exclusive and then this means mutually exclusive.
Okay, I think I like that. What happened is this one,
Yeah,
okay? It doesn't necessarily talking about non-mutually or mutually,
yeah,
because with non-mutually, with mutually, with independent, I can figure out this guy.
yeah,
But the bottom line is, if I understand the type of event, let's say for mutually, I know that this guy, the probability will be 0. Because for mutually,
yeah.
they don't have anything
They
in common.
can't.
They can't come together.
Yeah.
And what about the one that open up, the union? Okay,
Yes.
with union is, what is the probability that it's either this or this occur? Okay, the probability of this or this, if it is mutually, I'm going to say, okay, I'm adding this, I'm adding the probability of A, and adding the probability of B. If
Yeah.
it is non-mutually,
Yeah,
then
when it looks
this-
like that.
then I'm gonna have probability of A plus probability of B, and this is going to exist.
Okay. So if it's up, 'cause I understand now when it's down like this, but if it's up, it's when this and this happen,
Exactly,
can they occur but like not overlap?
exactly,
Okay,
exactly. So, but this one right now, okay, that union and interception, you know, what I wanted to also write down, the union and the interception, we can compute them, given any type of event. But the most important thing is, what is their job?
yeah,
Oh, this one is saying, this or that.
yeah,
This one is saying, do they have common stuff?
yeah.
Yeah.
Okay.
That's what it means.
When I looked at that, I was like, okay, I'm following what you're saying, but like these signs keep switching.
Yeah,
so, like,
it's switching.
let's
Yeah.
make sure we know what the signs mean.
Yeah, exactly.
So then when we see the signs and we
Mhm.
have an event, we know what
Exactly.
they mean.
Yeah, you know, that was what I was saying that time, like some students scare mad because of notations, like
Yeah.
they don't really
You gotta
understand what it
the
means.
notation.
Now you know that, oh, when I see something like look like a U, that's
Yeah.
like a, that, you know, okay,
That
look at,
means union,
look at that, union,
yeah, Yeah.
addition, union,
Yeah.
like coming together, you
Yeah.
are adding up. That's what it means.
oh, so every time that you have that
Union
sign,
is like
you-
something, so it means you are adding up. So you are only adding up if they are mutually exclusive.
yeah,
Then if they are not mutually exclusive, you add up and you also subtract that guy.
yeah,
Look at that. That's like a story. Is that not
It
interesting,
is
right?
interesting. I think the logic portion is very similar to like the kind of notations that
Mm.
we're using.
Oh, you have, oh, yeah.
Yeah, so
Mhm.
makes a little bit, but like I was gonna, cause I am starting to have like a little bit of difficulty with all the notations and stuff.
Yeah.
So on the exam, are we just implementing all this into our studio or do we have to?
Okay, that's a very good question. The exam is going to be a combination of our problem and not our problem, and that's why we're trying to showcase now in the
In the whole
assignment.
word.
Now you look at the assignment now, the current assignment, you can see how some parts are theoretical and the other part is hard. So that is the way the exam is going to be. But this is what we have been doing over the years. It's not as if you're going to bring your laptop, performing all of that, but we're actually going to make some kind of suggestions
Okay,
So next week now.
Yeah.
I'm gonna start uploading practice question for midterm one. So a class will be dedicated for that, where I'm gonna walk you through the problem, how you solve the problem. So our four of us upload question. Okay, I'm gonna say, okay, go and solve it. You are not submitting, you're not turning it in, you just want to, then maybe the next 2 days, I will upload the solution, then you grade yourself. You do that to prepare for the real exam, right? I do that all the time.
I
So
used to do that all the time. See, I took CIS calculus, or I took calculus here, calculus 1, and every time that like I did the homework and then they gave me the solutions, I would do it first and then I'd look at the
you look at it, you
solutions.
grade yourself.
Yeah,
I do,
because
when you do that, and if you're sincere with yourself, let's say for instance you do it, you're sincere with yourself, you score 95.
Yeah.
You will score more than 95 in the
and
real
then you
exam.
could like look at the walkthrough and you'd be like, okay, I got this, this, and this, but this is where I messed up.
Exactly.
So-
That's it.
and then for office hours, I emailed you about like another.
Yeah, when did you email out?
Yesterday, the day before yesterday.
The day before yesterday.
Yeah.
My at times it take 48 hours, so
Oh,
I can
okay.
assure you that
Okay.
reply to
Hey,
that.
I thought you was ignoring me, man. I
Ah,
was
no,
scared.
no, don't
The
be scared.
TAs are also open if you look at
Yeah, the
their-
TA
The only thing
also-
I'm worried about TAs is because like my economics class, I also go to the TAs too. Sometimes they explain it a little bit different. and I
Yeah,
have a
no,
hard
it's
time-
also good to hear from.
Yeah, but like
different
for our
kinds.
studio, I'm going to TAs as
Mhm.
well, so they're doing a good job.
They're in the same room.
Oh,
I
yeah?
just found that out. They're all in the same.
No, they are in the same room.
Oh, okay.
All of them. You don't.
They
Okay.
didn't tell us that. They just
Yeah.
told
But
us
you
that
have
this
a-
is the room they're
This
in.
is the room.
But they didn't say that they
are
were
in
all
the-
there.
They
You
are
have
on the same.
but you don't have a TA for lecture stuff, right? Just
No,
for
I
discussion.
have TA for this class 40 years.
Oh, okay.
For another, because I teach 2 sections of this class, so I have 8 TAs for this and for
Oh, okay.
And
Gotcha.
they'll explain probably anything in a lecture too.
Gotcha.
Yeah.
All right.
And lab is very, very essential to as passing assignment and the exam. So I would advise that you pay more attention.
Yeah.
Like I don't impose them recording, like whatever they do.
Yeah.
Yeah.
But I record my lectures.
Yeah.
So for students to have another opportunity. So
Yeah.
yeah.
All right, those are my
Rule
questions. So you have a
3.
good weekend, man. I appreciate you.
You're
All right,
welcome.
I'll see
Stay
you later.
safe.
All right, thank you.
Stay
man.
safe. Yep.
Rule 3.
Yeah.
It's like all this going on. What essentially does the whole equation mean?
Okay, so which one?
Rule number 3.
Okay, when you take a look at rule number 3,
Yeah.
this one here, okay, sorry, can I write something? I want to write, okay,
Do you want color?
yeah, I just want to write, maybe like, when you get it, okay. Oh, okay, now, this is what I'm saying. If I have so many events,
Mm-hmm.
maybe all the way to K,
Yeah.
okay, now, and I want to find the probability of their union.
Yeah.
Like I want to find the probability of E1 union, E2 union, blah blah blah
So
until you
that's
get up.
where the addition comes up and all
Exactly.
that.
Because
Okay.
this is just a generalization of the
It's-
2 events.
Yeah.
Okay, so if they are all mutually exclusive,
Yeah.
then we can just find their probability
By adding
for
them.
each, then adding them up, just like we
Okay.
said. That's what it means.
So it's just this big messy equation for something so simple.
Like
Like I see that all the time.
You can see what I used to talk about. Like today, don't really like if they can. That's why I like students who ask questions
Yeah.
because you want to be able to know this
Yeah.
equation that we have here. Well, what do they mean? By the time they tell you the meaning, you're gonna say, "Oh my God, this is simple." Then
Yeah. I know. Like
So
sometimes
that's
you
what it's saying.
overthink something that's very simple.
it's very, very simple. That's why I like teaching my course. Relating to real life, not just A or A1. When you go to some class, you're gonna hear, okay, A1, A2, they're just gonna be emphasizing on the equation, but that may not make sense until you relate that
Mhm.
to real life,
Yeah.
something you can see, something you can talk about.
Like for example, maybe like someone's schedule, like they have like this event, but then maybe their parents are at like something else. Like if you look at a family schedule,
Exactly.
you could have like multiple events being at the same time, but they might not all be there. You know?
They may not all be there.
Like you could be at math class, your brother could be at
Good
soccer
job.
practice, your mom could be at their job.
As somebody now say, what is the probability that you are in at least one? You are in at
Place.
least one that's going to be. It's either you are here or here or here. That is
Yeah.
addition now.
Yeah,
So that plus means or.
yeah.
So that's what it means.
Thank you.
You're welcome.
Have a good weekend.
And you too. Stay safe.
I will.
Yeah.